Good day and welcome. My name is Dr. DeForce and today we will cover the physiological functioning of the retina and vision. Starting with the outcomes, we will discuss renal anatomy, photoreceptors, and regional variation. Onto the physiology. As always, structure follows function. That said, let's shed a little light on retinal function, starting with the cellular layers of the retina. I have added a short excerpt from Guyton and Hall on your right, should you wish to pause for further clarification. Following the picture from the top, we start with a dark pigmented layer, followed by the rods and cones, or photoreceptors, sending their signals via bipolar cells to the ganglion cells that relay the information to the brain via the optic nerve. Horizontal and amacrine cells allow for the lateral communication and act as modulating interneurons, clarifying signals. Note, the direction of light penetrates through all these layers before reaching the rods and the cones. It might seem strange that the photoreceptors are the last thing light reaches. Why do you think the eye is built seemingly the wrong way around? Let's talk a bit about the two kinds of photoreceptors. The cylindrical rhodopsin-containing rods are very light-sensitive, differentiating between light and dark, and are by far the majority at 125 million. In contrast, the conical cones are sensitive to color, functioning in bright light. The approximately 6 million cones are primarily concentrated in the macula lutea, specifically the fovea, which we will discuss more momentarily. Cones contain one of three different photopigments for different wavelength sensitivity to respond to one of three colors. Both rods and cones synapse with bipolar neurons and use vitamin A for photopsin formation. Taking a look at the rhodopsin retinal photochemistry cycle of vision, rhodopsin is decayed into components like vitamin A by light interaction much quicker than the process can be reversed. Thus, you will adapt faster to increased light than you will to a decrease in light. As there are so many more rods than cones, and as cones need bright light to function, vitamin A deficiency often presents as night blindness. That brings us to color. All the colors that we see are made up of ratios of red, green, and blue. As you can see here, different wavelengths trigger different colors. Green cone deficient deuteranopes perceive the full visual spectrum, whereas red cone deficient protonopes have a shorter spectrum of visible light, just over 600 nanometers. Unlike green and red, blue cones are always present, but may, in rare cases, be underrepresented, referred to as blue weakness. The genes that code for cones are located in the X chromosomes, resulting in a higher rate of color blindness in men, who don't have the backup secondary X chromosome like women do, despite inheriting it from the maternal X chromosome. A supplementary link for color test charts will be provided should you wish to further explore the color blindness and its variations. Regional variation in the retina. The retinal surface is not homogeneous, and the rod and cone distribution differ with function. Following the path of light from the visual axis, the center of focus falls on the cone-rich region called the fovea and the macula lutea. The macula lutea tends to present with a different color as the type of photoreceptor changes. In the fovea, the cones are so densely packed that they're almost rod-shaped, outperforming the iPhone 14's 48 megapixel camera by an order of magnitude. The human eye is equivalent to a 576 megapixel camera. Moreover, the retinal layers associated with the fovea are located adjacently over the macula lutea instead, to decrease refraction and increase the quality and clarity of the image. Conversely, the periphery has more rods than cones, and your brain has several very interesting mechanisms that color your visual perception despite the lack of cones here. Retinal detachment, where the retina becomes separated from the eye, allows a short period in which the blood pooled between the layers may keep the photoreceptors sufficiently oxygenated to survive mere days, during which surgical reattachment may prevent permanent damage. The layout of the retinal layers necessitates a point at which blood supply and the optic nerve can leave the eye. The opening, called the optic disc, and the absence of photoreceptors in this proverbial doorway, results in a natural functional blind spot that your brain compensates for with information from surrounding photoreceptors as well as information from the alternate eye. Looking at this retinal photograph, can you identify the optic disc and the macula lutea? Consolidation. Here are a few questions with which to test yourself and facilitate memory formation. For further reading on these topics, consult Chapter 8 of Byrne and Levy's Physiology, as prescribed by the University of Witwatersrand. Information from the link will not be in the test, but provides interesting insight. Thank you for the opportunity to present to you.